Most of us learn the rules of gravity in middle school. Large objects pull on smaller ones. It's presented as a neat, invisible tether tying the universe together, governed by the elegant equations Sir Isaac Newton wrote down centuries ago. But that simple story hides a significant structural flaw. As you move into modern astrophysics, you encounter a reality that contradicts everything taught in the classroom. Gravity is not a force. The cracks in Newton's math first appeared right in our own solar system. When astronomers tracked the planet Mercury, they realized its path was shifting slightly over time. If gravity were a constant, predictable pull between masses, Mercury's orbit should have remained a perfectly closed loop. That mathematical failure becomes undeniable at the cosmic extremes. Inside the extraordinary density of a black hole, Newton's equations return infinite values, rendering them useless for describing reality. Because our foundational understanding fails to account for these specific orbital shifts and cosmic densities, we are left with a map of the universe that is demonstrably incomplete. To find the truth, we have to trace the history of the wrong answers that brought us here. For nearly 2,000 years, the prevailing explanation was philosophical. Aristotle argued that objects fell because it was their inherent nature to seek the center of the universe. This logic led to the assumption that a heavy object, possessing more earthly nature, would naturally fall much faster than a light one. That assumption survived until the late 16th century, when Galileo challenged pure philosophy with empirical observation. He took two objects of different weights, a heavy iron cannonball and a light wooden ball, and carried them to the top of the Leaning Tower of Pisa. He released them at the same moment. To the shock of the observers, both objects hit the ground simultaneously. By proving that physical bodies obey observable, universal rules rather than internal motivations, Galileo ended the era of Aristotelian physics and cleared the path for Newton. Newton's triumph was one of unification. He proved that the same mathematical principles, dropping an apple to the grass, were responsible for keeping the planets in orbit. Yet he had a blind spot. Newton could calculate the strength of the attraction, but he could not explain how that signal traveled across millions of miles of empty vacuum. Albert Einstein solved the transmission problem by rethinking space itself. He proposed that the void between stars isn't empty, but a physical medium that can be warped. In general relativity, a star doesn't reach out and pull on a planet. Instead, its weight bends the medium of spacetime, creating a deep geometrical curve. Planets aren't pulled by a force. They simply roll along the curves created by the larger mass. What we perceive as gravity is actually the geometry of that curve. Escaping it requires an extraordinary volume of energy, which is why a rocket must generate so much thrust to climb uphill out of Earth's reach. This shift upgraded gravity from a mysterious, invisible rope to the physical geometry of the universe, finally providing a perfect mathematical match for Mercury's orbit. Even Einstein's model has a breaking point. If you compress that smooth geometric grid into the core of a black hole, the mathematics of relativity eventually collapse into nonsense. This conflict is the central mystery of modern physics. While Einstein saw a smooth universe, Niels Bohr and the pioneers of quantum mechanics found that at the smallest scales, reality is jagged and divided into tiny, indivisible packets. In a quantum world, gravity cannot be a smooth curve. It would have to be communicated by distinct particles, messengers called gravitons. But physicists have never found a graviton. When we try to force quantum calculations into Einstein's smooth geometry, the results refuse to align. Our two most successful maps of reality are currently incompatible. If our best theories are documented as incomplete or contradictory, you might wonder why we still teach Newtonian gravity in school. It's because the schoolroom model is the necessary alphabet. You have to master the basic mechanics of how objects move before you can grasp the complex poetry of how space itself warps. Science is not a collection of static facts to be memorized, but an ongoing effort to identify the flaws in our own knowledge. The final, unified theory of gravity is still waiting for someone to ask the next great question.